Hi everyone. Good day, good morning. Welcome. I just want to quickly run down a few things before we start with our session today. Uh, I just want you to quickly have a look if your notifications are on, if you can just enable them so that you don't get any form of disturbance when you're trying to watch the session. So if you can just go to your settings and just ensure that you untick all the boxes so you don't get any uh, disturbance there. Just a quick one. I just want to check if everyone can hear me. If you can just put thumbs up, comment in the chat section. Perfect, perfect. Thanks, guys. Yeah, so let's just check out the notifications. Thank you. All right, so welcome to our another edition of EIT webinar. So today we'll be looking at the loop tuning with process control. This will be presented by Mr. Steve Mackay, who is our Dean of Engineering here at EIT. So yeah, these are just like common questions that we normally get from our audience. So yeah, we will be providing you with the copy of the slides and the recording. So yeah, just make sure that you check out your emails in at least 2 business days, and then yeah, have a look at your junk or spam folder. And then at the end of this session, I will be providing you with the QR code or perhaps a link that you can follow in order to claim your certificate of attendance for this program. And yeah, so we just sending out the certificate within the next 4 business days, obviously after this webinar. So just ensure that you stick around up until the end of this session. So I'll be providing you with the QR code in order to claim your certificate of attendance. And yeah, so just for those who are joining us for the first time, I thought maybe I'll just give you a quick overview about who we are. So at EIT, we specialize, we focus in engineering. So we deliver programs starting with our short learning courses, program micro-credential certificates. Those are 3 months programs. And we have diplomas, advanced diplomas, undergraduate, graduate certificates, bachelor's, master's, and obviously our highest level of qualification at EIT, it's our doctorate. And yeah, we're offering industry designed programs. So what you learn at EIT, we ensure that when you finish your qualification, you still have what the industry needs. And obviously, we ensure that we keep up with the trends. We ensure that our materials and also our resources are always up to date to ensure that what you learn is still relevant. So we just like any higher education provider in Australia. So we are accredited with the Australian government, and we also have uh, some of our programs that are recognized under 3 international engineering accords. So you'll get Dublin Accords, which is Advanced Diploma, Sydney, our bachelor's programs, Washington Accord, which is our master's programs. And yeah, we source our lectures from different parts of the globe. So our students get to sort of like have an global perspective of engineering. And also the benefit of that is that you get to connect with various engineers from different parts of the globe. And yeah, so we just making use of unique methods in terms of delivering our programs. We have, live interactive webinars. Students use our remote labs and simulations when coming to practical. So yeah, that's just a quick overview of who we are. However, obviously, if you want to learn more about EIT, you can always visit our website, EIT website, just to learn more about the programs and what we are offering. So for now, I'm just gonna quickly hand things over to Mr. Steve. I think Steve, you can take it away. Thanks very much.
Thank you very much, very much appreciated. Very delighted to be here today. Can you hear me okay, Barry? Is that okay?
Yes, yes, Steve, loud and clear.
Brilliant, yeah. Now you'll see you'll see my background is I'm at an airport, so there's a bit of background noise, but hopefully you can all hear me okay. I've done presentations at airports all over the place, and it just happened that I've just landed, found a place, plonked down, and I'm ready to roll. So let's go for it. So very grateful for Mr. Barry de Kotler. Um, extraordinarily good ambassador for EIT, always chatting, talking to our great students and obviously people like yourself. So I'm the I work at the EIT. Probably some of these comments are a little bit over the top. I'm not. I'm pretty low key. But really, what we want to do is go through a presentation today on um, loop tuning and some of the background to it. So that's basically the idea today. And I want to go through 10 tips for tuning loops. And really, I just want to obviously focus a bit on, first of all, the concept of tuning. And I know people get a bit bored hearing my voice, so I'm going to ask questions. So I just want to talk about the concept. I just want to talk about Ziegler-Nichols. It's always a bit embarrassing for me that we, as electrical or process control engineers, have Ziegler-Nichols who are mechanical engineers who put the whole basic building blocks for tuning together. A little bit academic, perhaps, but as Barry says, we'd like to focus on the practical outcomes as well. So then I'm going to spend a bit of time talking about closed loop and open loop tuning strategies, cascade loops, and dead time issues. I won't go into the dead time in too much detail with Smith's predictors, but just give you a bit of an idea. So we're trying to do the whole topic of loop tuning in 45 minutes, which is a bit embarrassing in terms of time. I'm trying to compress everything into 45 minutes. So I really want to go through the background theory and then obviously look at some applications. So it's really a little bit compressed, but you will get the slides and hopefully you can use YouTube or to actually get some more detail. So first of all, before I go any further, the whole purpose of this presentation is tuning of loops. Now, before we get too stuck out on things, I'm just going to share, just going to look at this little, oops, hang on, oops. We've got to talk about, hi, the guys joining, really good to have you here. So before we go any further, I just want to make sure we're all on the same page with the terminology that we're using. So the first thing is a set point, which you see referred to there. That means the target value. The target value. In other words, if I'm aiming for 30% level in the tank, that's the set point. And that will be really this little sucker over here, this fellow over here. This solid line. And let's just look at it. So the solid line here, that's the set point. So we're targeting that particular value. Then the other value, which is also really important, is obviously the process variable, this thing here, which will go up and going down. That's the process variable, PD. So we're going to abbreviate it PD, and I'll show you a loop controller in a minute. But the process variable. So obviously the whole idea is that your process variable settles down spot on with your set point. So there's a few targets or objectives with tuning. So tuning is obviously trying to control your level of a tank, and you've got a little loop controller, and we're going to look at all the activity around that. So the first thing is reduce the area of error. In other words, you want the process variable to get to the set point as quickly as possible. Now you can see this is what we call overshoot here. It's a bit problematic. And that also indicates a little magic term we're going to talk about in a tick called instability of the loop. So those are little issues which we will come to in a tick. So don't worry too much about it. And the other item which I haven't mentioned is, of course, the output from the controller. Output. So output is the other one, OP. So we've got output, process variable, and set point. So the first target is try and get that area as small as possible, which means get the process variable to fit into the set point as quickly as possible. And another one is minimize amplitude area squared. Sorry, I'm just jumping around a bit here with my computer. This next item is minimize wear and tear. Now, why would that be an objective of tuning? What's wear and tear? What am I referring to? Can you please tell me in the box? You'll see a little box there, this text in there. Why do we want to, so I'm trying to reduce wear and tear. What am I referring to? Why should that be a problem? Please text it in the box. Yeah, okay, that's a good point. Connor, as Connor says, turning a pump on and off is too much. So we're trying to fill in a tank, and then we're using on-off control for the pump. Hey, on, off, that's the surest way to burn out your contactors and your pump to damage your pump. It's generally referring to situations where you've got a valve. Yep, that's right. Thanks, Fres. Brilliant. So typically, when you look at a valve, oh, we've got a huge number of comments. Brilliant. Thank you very much. You people are all teaching all your chums here. Fantastic. Wear and tear for the valve. If valve is not setting down the control, reducing wear and tear to make operations smooth. Absolutely right. So a valve, for example, if we're trying to target a value and we keep tweaking the valve from 52%, 51, 52.5, bingo, 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 it's obviously not a good thing. And then the other targets with tuning, not always the case, but no overshoot at startup. Why would that be a problem? No overshoot at startup. In other words, when you're filling a tank, you don't want overshoot. Why would that be an issue? No overshoot at startup. Why would that be an objective? Avoid mechanical failure. Yep. So the next question is, why no overshoot at startup? Why would that be a target? Yeah, absolutely. As Connor says, thanks, Connor. You've got a lot of common sense here. As Connor says, we've got a tank, and for some amazing reason, let me just sketch this in here. You've got a tank looking like that, and we're targeting a 95% filling. 95%. We want to get it up to 95%, and of course, sorry, my 95%. And we want to get up to 95%, and of course we want to make sure it doesn't go to 98, 102%, and of course overflow the tank. Or you, worse than that, you pressurizing a cylinder with gas, and then you don't want to overpressurize it, otherwise you may stress the components out. So no overshoot at startup. Obviously not always the case. And then minimize effective known disturbances. And this effective known disturbances is a really, really important thing. When you're working with plants, factories, industrial plant, your operators know so much about the plant. You should always kowtow to them. Hello, how's it going today? What disturbances are there? They often know about disturbances which you have no idea about. But your tuning may be to reduce that effect of those disturbances which the plant operator may tell you. So those are sort of objectives. That's what we're trying to do with this loop tuning. Now, there's a little diagram here which I just want to pull out, if I can find it. Yeah, here's the diagram. Now, this diagram here summarizes the whole theory behind what we're talking about. And I must say, I went to university and I studied process control until some old, hardened, experienced guy pulled me aside and said, "Hey, Steve, I'm going to teach you." And he taught me everything I knew about process control. Unfortunately, uh, the theoretical courses didn't really help much, but he had the experience and he taught me, a guy called Wolfgang Altman. Unfortunately, he died of motor neuron disease, but amazing guy, really incredible. We should celebrate every day we have. Now, this is his diagram here. And I just want to summarize the whole of the concept of process control with this diagram. So the idea with this diagram, let me just get my mouse running, is this is your controller over here. That's the controller. That's the sucker that we are trying to tune. We want to put parameters in there. We want to put a gain, a we call it integral time constant, and a derivative time constant into that controller. So the controller then has an output. It comes out, and we have a set point and a PV coming into the controller. So this is all part of the controller. The set point we've already spoken about is the target value. The process value, that variable is the value that you're measuring. It could be a temperature, pressure, level of a tank, who knows. And then you've got the output. And then, of course, this is the process. This is the process. This is the animal that you are trying to control. This is the thing that you're trying to deal. Now, don't worry about all these little squiggles and things here. Just understand that it's like the process controller has an output, and the output feeds into the process. So this could be controlling a valve, for example, a little valve. Could be controlling a valve or something like that over here, or a pump or something like that. And then you measure the output from the process. This is a single loop, of course. We'll talk about cascade loops where one loop feeds another. But this is the process, and that's the animal that we're trying to control, and we want to try and keep it in a good stage. Now, you'll see all sorts of little squiggles here. I just worry too much about them yet. I'll come back to that in a tick. I just want to make sure we're all on the same page. So we deal with PV, process variable, set point, and of course the output. So those are the three things we are going to be looking at now. Now, the issue, of course, is with this controller, we're going to do what we call open loop control first of all. I'll come back to that in a tick. And this is the techniques of control, which we're going to look at. Some of them are a bit academic and others are not. Now, if you look at this loop, let's have a slow think about it. What you will see is, let me change my color as well. Try and sign some red. There we go. Okay, so we've got red here, and this is the output signal coming out here. And as you can see, I've got a representation of a sine wave here. What a disturbance. Okay, Francois, good question. I will come back to all the questions at the end, if you don't mind, just right through the middle. A disturbance could be a variation in something in the process. For example, you may have a conveyor and you're weighing a material in the conveyor, and there could be some issue with the conveyor. Someone puts some extra material in the conveyor that could disturb your control factor. So disturbances are things which upset the process, and your controller must be able to deal with those. So we'll come back to those in a tick. So you've got the output here, and as you can see here, we're trying to show you the phase issue. Phase is really important here. So we want to try and draw on the fact that with this phase shift, you can get instability. Can you remember the days that you're on a microphone, talking into a microphone, hello, woo, and you've got a speaker next to you? When you speak on that microphone, you have your sound coming out of the speaker and you get a feedback loop occurring. And it often creates instability because all of a sudden the noise gets louder and louder and louder. That's instability. And we're trying to show you the same thing with this diagram here. It's exactly the same thing. We have a feedback loop. So what we've got here is a output here, which is the, look at the black there, and we've got a disturbance comes in, and the process has a 180-degree phase shift. Why do I say 180-degree phase shift? I'm trying to write this out here. I'm sorry, it's a bit scribbly. So we've got a 180-degree phase shift across the process. Why should that be? Can you see here? I've gone from this black here to the black on the top there, a 180-degree phase shift. And as Lance says there, disturbance could be a higher demand of steam causing drum level to drop, anything to make the PV drip from the set point. Thank you very much, Lance. Brilliant. So a 180-degree phase shift. Why should you have a phase shift in the process? Any comments? Any suggestions? Yeah, reverse hacking. Yep. Okay, we've got discussions about disturbance. Please look at the text on the side. I've got an incredible amount of really, really knowledgeable people making comments here, which are really powerful. So the 180-degree phase shift could be something like a temperature loop. When you heat up a tank of water and you measure the temperature, do you see an immediate heat and then 100 degrees Celsius? No, you don't. It takes time. That lag is where you get the 180-degree phase shift. So there's a delay in the process. Any control action, there's a delay. And then we feed this back here, and we still got there because we've got no phase shift along this part here, and we feed it in there, and it comes back, and you can see it's now been inverted again. And the reason why it's been inverted is because you've got a negative here in the process. So we've got set point minus PV, and of course you've got negative, and we then invert this. So basically what happens is that when you've got a 180-degree phase shift here, then the signal goes around the loop and it tends to reinforce the output. So it gets bigger and bigger and bigger. Obviously the gain, and that's the other number we must talk about here, the gain is the multiplier that we have for the process. If the gain is 1 or greater than 1, then the disturbances will tend to be amplified. If the gain is less than 1, even though you've got a 180-degree phase shift, the disturbances are minimized. Thanks very much. And thank you very much for all these wonderful, wonderful comments here. Brilliant. Time is tight, and I know Barry will be shaking me up now. So the first method is changing the output of the controller. So that's the output here. Changing the output of the controller and looking at the result. So there's your output of the controller. Boom. So it's in what we call manual mode, and I'll come back, I'll share an example of a loop controller in a minute. It's a little bit ambitious, but I'm going to do that. So then we make an output change, and you can see the process has some delay. There's a delay. Process has a delay. Oops. Process has a delay, and then it moves up. So for example, I'm heating a tank of water. I've turned the temperature up. We've increased the heat on the boiler, and it takes a delay. And there's two numbers here we use to do our calculation of tuning constants. One is what we call the effective lag, which is the delay there. You can see that there. And the slope. The slope is actually, this is the process variable, is actually the distance of that over the rise over run. So slope's obviously important, and for those of you that are mathematically inclined, you'll know it's a derivative. So this is called a reaction curve. This is the result of the output. So what we then is the result of the output. So what we then do is we plonk those numbers in, and this is what we call open loop controller. You can plonk the numbers in and you can have three forms of control: P, PI, or PID control. Now, I don't have the time to go into the precise differences, but I would ask you, what is the most common form of process control? What's the most common form? Is it P, PI, or PID? No, 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 no. PI, PI, yeah, PI. So we always refer to as PID. Oh, thank you. Yeah. Thanks very much, guys. That's wonderful. And ladies. Yeah, so PI control is the most common. Why can we not use P control on its own, proportional control? So one's proportional control, one's proportional integral control, and one is proportional integral derivative control. Why can we not use proportional control? Absolutely. As Lance says, what happens with proportional control on its own is if you only had a gain, and this KC is called the gain factor, that's called the gain factor. That, unfortunately, on its own is always make sure that when you set the tank level to 82% as my target value, my target set point is 82%, you'll always get your process variable to go to 83 or 84 or 80%. It'll never get to the target. And as Lance says, it's because of the offset error. There's always a bit of offset. And how do we get rid of the offset? What do we add to the mix? No steady state error compensate. Yeah, exactly. Thanks you very much. Thanks so much. So what you do is you add integral. So this is the little diagram that we have. Thank you very much, everyone. We've got your set point there. That's our target value. And this is the process variable, PV. That's the process variable. Sorry, it's like a drunken scroll. Process variable, and what we do is we use integral control, and it actually integrates out that error there. So there's a bit of an error for process variable and set point. As you know, integral actually grabs the bit of error, and we then use that bit of extra effort into our controller to drive it down to process variable to match up with set point. Absolutely right. Now, why on earth would you ever have PID control then? Surely PI is perfect. Why would you use PID control? Yeah, that's true. But where's a very obvious example? Yeah, it does speed it up. Yeah, that's true. But what's a typical loop with? Ah, thank you very much. Thank you very much, Matuluzi Malazi Tenga. Thank you, absolutely right. So when you got temperature, and I want to just reflect on this, and I know we haven't got much time, but I just want to reflect on this thing here. So here we've got the controller and the process. Now, when you have PI control in this thing here, unfortunately, integral actually adds a 90-degree phase shift. It adds a 90-degree, it's like a capacitor and an inductor. So you have a 90-degree phase shift. Unfortunately, it's a lagging phase shift like an inductor. So what you do is you add derivative control to actually cancel that I out. And it is because when your process has a temperature loop has a lot of lag in it. So when you have PI control on its own with a temperature loop, you actually adding a lot of extra lag in, and you could push your loop towards instability. So by putting derivative control, you cancel out that I part, the 90-degree lead cancels out the 90-degree lag. So you actually get a nice settling out of that. So you can always look at this whole thing from the point of view of stability of the loop. So the loop is stable, and you can push it closer to stability by putting derivative control in for a temperature loop. Fortunately, most of our loops are not slow moving, they're fast. And probably the best example of a fast-moving loop is what? What loop? Where would you never use derivative control in the loop? What's the most common example of flow? Thank you very much, Lance. So derivative control would be unlikely to use with flow, as I'll come back to the end, because flow is very quick. So once you have a quick change to your valve, you measure the change immediately. There's no lag. Whereas when you heat up a boiler with water in it, it takes time to see the heat, the temperature going up, and of course there's a lot of lag there. So the issues here are we can use open loop control, or we can start looking at, this is a nice clean slide, we can start looking at closed loop control. And with closed loop control, let's just move on to that. We have what we call the Ziegler-Nichols form of control. I don't know where the actual Ziegler-Nichols is here, but it should be on the slide. Ziegler-Nichols, and Ziegler-Nichols is probably the most famous example of, and there's some very good comments here, by the way, very good comments on the side. Please read these comments. You've got another 134 people teaching me and your peers. So thank you very much. All those wonderful comments coming in here. So the most famous example that everyone talks about, which is unfortunately completely impractical, but it's a very nice consideration, which is called Ziegler-Nichols control. And this, what we do here, is we put the controller into P control only, and we then put the controller into automatic mode. You make a step change, and then you double K until you get continuous cycling, and then you calculate the tuning constant. So this is what we do here. Here's the process, the loop. Put it into proportional control only. Why don't you put I and D control in your controller when you're working out tuning constants? Because you're going to actually upset the calculation, because as soon as you have I and D in your, when you're trying to work out what your tuning constants are, you will actually upset the calculation because you're adding a phase shift, phase lag into it. You're trying to find out what the actual process phase lead, phase lag is, what the lag is. So with a process, you're going to be looking at your, oops, sorry, I'm just so useless with the screen. My mouse jumps all over the place. So here's the controller. So with Ziegler-Nichols, you are looking for marginal stability. You are looking for a cycling where your output cycles like this. This is what we're looking for. Now, this is what we're looking for, a cycling there. So the whole approach here is to increase the value of the gain of your controller until such time as you get this cycling effect here. Now, my question to you is, do you think that's practical? Do you think your boss is going to say, hey, buddy, mate, just go and tune the loop and just run it into instability? Even if it's marginal, you have your controller going up and down like that. No way, Jose. Are you mad? You're not going to be putting my loop, my process into marginal instability. No. So this is a good idea, and it shows you the concept, but it doesn't actually, it's not a very practical way. It is a practical way based on this. So the idea here, we take the Ziegler-Nichols as the concept, and then we look at a modified version of that to get the best version. So you've got P control. If you only got P control, and this is with those constants you've got a KU, which is the value of K that you got when you had marginal stability. So when you had that cycling going on, you had a gain value, which we call the ultimate gain value, K. And what you do is for only P control, you say 0.5 times KU. Do you, as a matter of interest, we keep going on about proportional control as an example there, and then we say you can't use it. Does anyone use proportional control on its own? Do you think it's useful or not? Just on its own. Any suggestions there whether it's useful? Look, I always remember working on a gold mine, a gold plant in Kalgoorlie many years ago, and I was trying to tune a loop for a level in a tank, slurry tank, and the guy said, the electrician came up to me and said, "What are you doing?" So I said, "Oh, I'm just trying to tune the loop." He said, "I don't care whether the loop's 50, whether the level of the tank is 55% or 60% or 50%, as long as it's not overflowing or it's empty, I don't really care." So proportional control is probably more than adequate for that. So don't, you don't, if you're not wanting a precise control, who cares? Proportional control does. But most of the time we'll be using P control. Now, can you see with P control here, we've actually got a slightly reduced version of the gain. So instead of 0.5, we've reduced it to 0.45. Why have we done that? Well, the reason is because you're introducing a little bit of instability here with a 90-degree phase lag with your integral control. So the integral controller does add a bit of lag, and it pushes you closer to the instability region. So you pull it back by going for a reduced version amount of your gain. And then with PID control, if you're looking at a temperature loop, for example, you can see that we've increased the value of the gains. We've gone up more because this derivative control here actually gives you, pushes you towards stability. Because once you've got derivative control in there, you're actually pushing in 90-degree phase lead. So you can actually be a little bit more aggressive. Yep, thanks. We've got some really good articles here. No audio from the presenter. I don't know. Can you still hear me there, Miss Berry? Can you still hear me?
Yes,
Oh yeah. Okay,
yes.
thanks.
I'm
Okay.
just gonna advise
Thanks.
Rodell, maybe just
Sorry.
check your audio.
Yeah, check your audio, guys. And we're going to give you a bunch of slides and the whole recording after. So don't worry. Unfortunately, time is tight, so I can't hang around. I'll get kicked off very, very soon. So we had a discussion about lags and leads. This is actually these are quite useful slides. I'm not going to go into those now. And first order response curves. These are response curves. They're really important and they're really good for modeling. So what I was saying is Ziegler-Nichols with oscillations like that is a good idea in academic terms, but really you're not going to let your boss is not going to let you run your plant in cycling. So what we do is we try and have a damped oscillation. So we create a damped oscillation, and then from that we work out our tuning constants. And the way to do that is simply don't go into instability like Ziegler-Nichols. So what we do is we go for a loop response looking like that. Can you see here, this guy here goes up. So this is the response of the process variable when I've made a step change. Goes up and then it drops down and then it settles. So this here is what we use to work out the tuning constants. With Ziegler-Nichols, what we're saying there is we go and we get the loop to go like that, which obviously is not a good idea, as I said. So we go into this arrangement here where you have a bit of an overshoot and then we work out the tuning constant. So you have overshoot V2 over V1. You see V2 over V1, VK ratio, V3 over V2. And from these, we actually calculate some constants. So you actually end up with a calculation looking like this. So you put the control into P control, as we did before, put the control into automatic mode, double cancel oscillations, terminate immediately so you don't have a continuous oscillator. All you get is that overshoot, and then you work out your tuning constants. And then you convert your period from that. Now, some of you may say, well, what's the period? Yeah, I'll just quickly show you. So a period would be the distance like this. So a period is one full cycle of the wave, like that. That's one period. Okay, so from this, you look at your response curve. So for example, if it's delta 0.25, you're going to get, if you get a delta of 0.5, for example, like that, that's your damping. Like that, 0.5, you can see the curve, it's slightly average, so 0.5, so we go up like that. And then we multiply our, sorry, I'm just trying to, jeez. Okay, so we're trying to just look at there, and then you look at your PU over, so that's 0.75. So in other words, what you say is your period over P is 0.75. And then you can work out your tuning constants from that using this formula here. So you can work out PI control or PID control using that, with RD is PU over P. So that's where we get the delta. We use the delta to work out what R is, and you plug it in here. So that modifies your initial calculation, and then K determined by good judgment. Obviously, when you work out your gain, you make sure that you're quite far away as possible from any instability, which is like that. And then there's a few other tuning constants that you'll use. For example, here you'll see if you want no overshoot at startup, you want your process variable just to creep up slowly. Can you see here you've got a really, really low value of gain. The gain here is extremely low, and it's because you want to try and be as conservative as possible. And obviously your integral and your derivative control, you want to try and make sure that you are as conservative as possible so that your process variable just creeps up. So the other items, and as I said, I'm very conscious of time. I just want to spend a bit of time talking about cascade control and delays, dead time. Dead time is the killer for any decent PID control. So cascade control, I just want to spend a bit of time talking about, and that is a single loop there. So you can see a single loop. And before I go into that, I just want to just do a quick share, if I can. Oops, let me just see if I'm going here. I'm just going to try and show you a live controller, share a live controller if I can. I know time is tight, but I'm just going to try and squeeze this in. Here we go. That's it's always a bit of a tricky bit trying to do this on the fly. Let's go to that. Okay, here we are. So I've got a lab. I've got a simulation running here in one of the labs. So let me just go. I'm just going to share this with you. Hopefully you can see the screen. Gary, can you see? Can you see this? Can you see a different screen, Barry?
Not yet, Steve.
Sorry, I'm at Shark Airport, and of course it's some slow bandwidth. Shark Airport, and of course it's some slow bandwidth here.
Yeah.
I'll probably
Now
run
we
out
can
of power
see.
soon as
Thanks
well.
very much.
Ah, excellent. Okay, thanks very much. So, unfortunately, I'm going to run out of power soon, so I've just got to, and obviously time as well. Here's a typical example of a controller. Can you see the controller here? Can everyone see this controller? Let me just okay, so here's the controller. Now, what I want to show you is literally here, this is all the stuff about tuning constants I've been talking about. Here are the tuning constants. Can you see there? Gain, reset, administer, repeat, derivative. Now, as you can see here, the reset value is 100. So you say, well, that sounds like a lot. That means that effectively your integral control is basically almost zero, because it's 1 over T int, 1 over the reciprocal. So 1 over 100 makes a very small action for integral control. And 0 is of course 0. Now, if I, and I've got the loop in, I can have the loop in manual. So if you can see here, if I just, yeah, clear, clear. Okay, I'm just trying to get onto the manual mode. Okay, so manual mode here, if I change the set point here, you'll see very little change happening. When I put it into automatic mode, I think I may have a problem here with the actual access. Unfortunately, it's a bit slow. Yeah, it's a bit slow, unfortunately, but unfortunately, I can't really get that lab. It's a bit slow out here. Unfortunately, I'm on a very slow link. I'm just trying to go back again. Just see if I can get this going. Okay, yeah, it's running again. Barry, can you see this or has it dropped out?
Yes, we can still see the screen, Steve.
Brilliant. Okay, thanks very much. Okay, so here we've got it in automatic mode now, and as soon as I make a change to the set point, of course, the output does all sorts of changes, and obviously it's driven by this tuning constants. So if I make a tuning constant, say 100, or no, we won't go as much as 1,000. Let's go for 100. Let's go for 100, which obviously is totally ridiculous. But if I go to that tuning constant and then I make a change, can you see, as soon as you make a change to set point, you get instability. So instability is the output going berserk. And can you see that this is getting bigger and bigger and bigger, the actual process variable. So obviously the trick is to avoid that by keeping your gain as low as possible. But obviously if your gain is too low, it means that your process variable doesn't follow your change in your set point quickly enough. Okay, unfortunately time is tight, so I'm just going to quickly go back to the loop tuning. Let's go back here again. Okay, let's go back. I've just think I've lost the slides, Barry.
Just a sec.
Sorry about that. I've just lost the slides by going there. I think it's because I've got a very slow link here. Thanks. Sorry about that. Okay, just two last topics I want to spend a few minutes on because I know time is tight, and that is obviously cascade control. Sorry, I'm jumping across. One should be very careful about doing that when you've got a very low bandwidth link. Okay, here we go. Okay, so the cascade control is what I just want to spend a few minutes talking about, and that is, so cascade control is what we want to talk about, and let's get rid of that. Okay, so cascade control, you've got a temperature loop there, you're all very happy, and it all seems to be going well, and we've tuned the loop perfectly. The problem that you may have is that the fuel itself may have some issues with disturbances. So the pressure of the fuel fitting in here may be varying, which means that, of course, your flow rate changes, and, of course, you have uncontrolled things happening to your process. So here, your inlet temperature is coming in, blah, blah, blah. Here's your outlet temperature. All you're doing is, as soon as you see a change in the temperature, your target value, you adjust the valve. So you may say, look, I'm going to do some control of that valve, and I need to create a cascade loop. So this is the classical application. Can you see what we've done here? We've taken the original loop, this one here, the primary loop, and we fed it into a cascade loop, another loop here. So you've got your output from this loop feeds into that one there, and you're now controlling this loop here with a valve, which is fine, you've done that before. But in addition, you're measuring the flow rate, and you're using a flow rate to actually control the valve here. So you've got basically an action happening here, and obviously you've got your original loop over there. So that's a cascade loop. temperature controller into a flow controller. Now, with a temperature controller, you would probably be using PID control. With the flow controller, as we said, because there's very quick action, you'll be using only PI controller. So here's cascade controller. Obviously, be very wary of stability. And unfortunately, one of the problems when you walk onto a plant, if you ever walk into a plant, you'll often see the cascade loop put into what? Cascade. Often you'll find it actually are over here. And I think some guys already commented there. Cascade controller, mainly a flow controller, the secondary. So the guy at the bottom is the flow controller, what we call a secondary controller, and the temperature controller at the top is the primary controller. So that has to be PID because there's a long delay before you see any changes happening to your temperature. Whereas with flow control, as soon as you make a change to the valve, bang, you see the flow change immediately. There's no lag at all. So PI control. Now, the giant killer and what makes my whole presentation to you completely worthless is, of course, dead time. Dead time is public enemy number one for loop control. So that is what I'm closing on. And I mean, it's terrible to close it on a destructive thing like that. So dead time, what is dead time? And can you give me an example of dead time in the text box? I know we're running out of time here, and I'm running out of power. So dead time could be something like this. Yes, yeah. Oh, yeah. Thanks, Lance. Thank you very much. Lance has just introduced my slide. In fact, I think Lance needs to present this. So here we have a conveyor. Here's the conveyor running happily. It's got a feeder. We're feeding onto the belt and measuring the mass over here. So from the time you're controlling the feed to the time you measure something, there's a delay. And you may find that you have an unhappy delay. So as soon as you make a change to your feed onto the conveyor belt, you measure the change and you say, hey, there's no change. So what do? You put more in, and more and more and more. And of course, then suddenly you overshoot and then you have to start reducing again. So it's dead time is public enemy number one for a good PID loop. So there's two strategies here. One is obviously using more sophisticated control or just having a very slow acting loop, which is probably the typical one. So there are challenges here. Thanks for questions there, but suggestions is to detune the controller for a slow response. Or you would see the problems of your controllers, you see instability in the loop. The other one is you use a Smith predictor. And what a Smith predictor really does in essence, and I've taken that slide out because it's quite complex, although I do love explaining it. We don't have the time to do it. But what a Smith predictor does, it models the process. It models the process that you've got there, the delay. And what it does, the Smith predictor strips out the delay. So as soon as you change the feeder from 50 to 55%, your controller immediately reads back through the Smith predictor what that response would have been. So we take the delay out. That it requires you to have a very good model of the actual process. If you have a poor model, you're wasting your time. It won't be a very happy response at all. So, and thanks very much for the comments there. We've got a lovely one there. Dead time is time lag between input signal change and the instrument's response to the change. Yep, that's right. Thanks. Okay, so that really gives us to the end of the session. I'm sorry to overshoot, but it's just 2 or 3 slides I just want to mention quickly. Just from a practical point of view, level control. You obviously want to maintain the flow as quickly as constant as possible. Medium response, tune as slowly as possible. So that's pretty straightforward. Flow control we've spoken about. Here's flow control. aim for fast response, no lag in this. Between the changing the valve and measuring it, you won't see any, well, you shouldn't see any lag unless you've had your flow meter very far away from your control, your valve. And temperature control, unfortunately, lots of delay, major process lag, and dead time in the system. So you tune as quickly as possible without causing oscillations, and you'll be using PID control, not PI. Okay, so I just want to thank everyone here for attending the session. I'm almost out of power, so thank you for bearing with me. My screen jumps all over the place because there's a bit of latency. I'm connected up to my phone, a hotspot. But thank you so much for all your incredible comments. In fact, I've learned more from you than you've learned from me, and you've got a really fantastic bunch of colleagues here who have been so sharing of all their knowledge. So thank you so much. Really appreciate it. If you have any comments, please send them to me. And thank you for educating me on PID control. Thank you so much. And I'm sorry to overshoot a bit. Over to you, Barry. Thank you very much.
Thanks very much, Steve, and thanks very much for everyone for joining. So just look at some of the programs that we have at EIT that were sort of like resonate with the topic today. So like I mentioned, you can always just visit our website to learn more, or otherwise direct all the queries that you might be having, and then we are happy to assist you. And also just adding into some of the upcoming courses that we have. So yeah, if you can just go to eit.edu.au, then you should be able to see all the programs there. And this also include upcoming webinars. So if you are interested in some of these topics, just feel free to go and register so you don't miss out. And yes, so I'm just going to quickly give you a moment to, if you can just take your phone and ensure that you scan the QR code. For those who are not able to do so, I'm just gonna put in the link. So just a sec.
And while you're doing it, I just want to thank Mr. Barry de Kotler for choreographing this. Thank you so much, Barry. Barry travels all over Africa and the world, talking to our incredible students and engineers in industry and stuff like that. Thank you very much for giving up your time to shepherd me through this presentation from Durban
Thanks, Steve.
Airport, King Shaka International. Thank you very, very much. Really appreciate it. And I hope you all have a marvelous afternoon, and hopefully it's warm for you wherever you are, not freezing cold like Cape Town is at the moment.
Thanks, Steve. Okay, and just one last note. Please note that this form will be closed on Monday, the 18th of July, around about 5 p.m. So, 5 a.m. So just ensure that you request your certificate before then. Otherwise, we will no longer be accepting any request afterwards. I'm just going to paste the link one more time. Thanks very much. I think that's about it. And once more, should you have any feedback, any form of suggestions, please feel free to send us an email, webinars@eit.edu.au. So feel free to share all your input. We would really love to hear your comments, your feedback, or your suggestions. Otherwise, thanks very much. Thanks very much again, Steve.
Thank you. Thank you very much. One and all, have a wonderful day, Wednesday, and thank you so much, Barry. Really appreciate it. See you soon in
Thank you.
Joburg.
Bye.
Thank you. Cheers. Bye. Bye.